ISO, where she has been involved in different projects and in the last years in the ALMA Regional Center. And she was the acting director of that center in the last time. Now she's not anymore doing that administrative tasks in many cases. So she's free to work on what she likes, that is active galaxies, quasars, high-redshift quasars, etc. But today she's going to talk about the last upgrade of ALMA, and that's the wideband sensitivity, the wide sensitivity upgrade, WSU. So thanks a lot, Evanthia, for being here with us.
Thank you, Ismail. I already have one, I think. Okay, well, thanks. Exactly. Okay, thanks very much, Ismail. Thanks everyone for showing up. Indeed, I'm here for 1 year to do what I like, which is quasars and AGN and stuff, but maybe for this we'll talk at some other time. But I thought of taking this opportunity to bring you up to speed with ALMA's first and most important upgrade. So ALMA has been operating since 2011, 2012, formally since 2013. And now we're undergoing a major upgrade. So I want to talk to you about this and hopefully make you realize what this upgrade means in terms of science throughput once it's done. So indeed, I will be here until summer under what ISO calls research period. So I'm allowed to do science and no management duties. So I'm very happy about this. And putting together this talk, I shamelessly took material from my colleagues, John Carpenter from the JEO, Martin Svan and Maria Diaz-Trigo from ISO, as well as stuff that I put in myself. So almost everything is stolen, but wanted to acknowledge that. And of course, the Fundación Occident that is funding the first month of my stay here. So in this presentation, I'm going to talk a bit about everything. So I don't want to jump into the WSU directly. I want you to go through, what ALMA is, how we are, the science it is producing right now, and then how, via the developer program, we have reached the stage of the wideband sensitivity upgrade, and a bit about the future and the new science that will come out of this. So when we talk about ALMA, I think all of us have this in mind, right? It's many 66 in fact antennas working together, a big interferometer, the largest submillimetre facility on Earth right now. But in fact, ALMA is a lot more than that. And this is important when we talk about the upgrade, because you have to realize what ALMA means in terms of installation infrastructure in order to understand the magnitude of the upgrade that we are embarking in right now. So apart from the antennas at the 5,000 meters, we also have the technical building that is hosting offices and spaces for people that are working there for maintenance upgrades and stuff, as well as the correlator. So the correlator is the heart of ALMA, is the massive computer that is actually correlating all the signals that come from the antennas. And it currently lives at the AOS, the high side, at 5,000 meters. Now at 3,000 meters, at about an hour drive from the high side, we have the OSF, the Operation Support Facility, which hosts the Residencia, the maintenance building, safety buildings, and the control center that you can see up there. And this is yours truly in one of my shifts up there. The operations were run from the OSF up until the pandemic, exclusively from there. So we had to go up the mountain, run all the operations day and night from there. But I will say, thanks to the pandemic, in fact, we now have moved the operations, or most of the operations, down to the offices in Santiago at the JEO. And this is the new control room at the JEO, where we run the operations during the morning and the day, and the night shifts are still run from up the mountain. ALMA has three partners, three executives, as we call them. So this is ISO with its member states, North America and East Asia, and of course the hosting country, Chile. So this is also very distributed, or well, worldwide distributed, and of course the users are coming from all over the place. So anything we touch has an immediate impact worldwide. And this is just a global distribution of everything that ALMA has to do in the world, in Chile and up in the Atacama Desert. So ALMA was built with 3 original science drivers in mind. We didn't do it because we could do it. We did it because we wanted to do it in order to address these 3 science questions. So we wanted to have an instrument that has the ability to detect spectral line emission from CO and C+ in a normal galaxy like our own outer redshift or 3 in less than 24 hours observations. We wanted the ability to image the gas kinematics in solar mass protoplanetary disks at a distance of 150 parsec, and we wanted the ability to provide precise images at angular resolution of below 0.1 arcsecond. And in fact, in the first 10 years and a bit of ALMA operations, we have achieved, in fact, all of this. I just show here 3 examples, one for each case. So Aspects is one of the first large programs at ESO. Large program means more than 50 hours of ALMA time. And this large program was a blind survey scan for CO and dust in the Hubble Ultra Deep Fields. And this is actually the deepest CO and continuum observations over a contiguous field ever carried out with ALMA. Some of the results of this is that more than 93% of the dust attributed to galaxies has now been resolved. We also found out that the molecular content of the universe has decreased by an order 6, a factor of 6 from redshift 1.5 to now, and many other things that came out from projects like this. On the second topic, on the ability to image the gas kinematics, this is an example of a deviation from a Keplerian velocity on a protoplanetary disk around a young star. And this is attributed, this is a bit old result, but it's still quite spectacular. This is attributed to the presence of a 2 Jupiter mass planet around this star. So already this science question also answered. And last but not least, I'm sure you've all seen the spectacular images of the HL Tau and similar. So this is a protoplanetary disk around a young star. This was first observed as in campaign mode, long baseline mode back in 2014. In resolutions that go far beyond this one. So we've reached, depending on the bed, from 0.075 arcseconds to 0.025 arcseconds. This corresponds to about 3.5 to 10 astronomical units in this. So these gaps here, as you know, they are believed to be formed as galaxies are formed and are swiping the material around them, and they are leaving little gaps as they go by. So this is a young star. It's like 1 million years old, and is forming a planetary system that will be about 3 times the size of our own. It's quite spectacular things. And of course, a lot of science cases have been built on top of that. So in principle, take on that as well, ALMA has already achieved what it was built to do. So it is really a most productive instrument. It has observed everything from our sun. This is a map of the sun in band 6 or 230 gigahertz all the way to the beginnings of the universe. This is oxygen 3 detection at redshift 9.11 galaxy, and for a while this was an absolute record. As you will see, it's no longer, and really everything in between has contributed to the Event Horizon telescopes, and it has observed pretty much everything. So it has achieved what it was built to do, and it's still achieving more. So I wanted to present like a summary of the scientific achievements of ALMA, or scientific output of ALMA in the past years, but then I got stuck with 2024, because only 2024, we're still producing the first, the best, the largest, the whatever you want, it is there. So I'll just focus on a few results that were produced this year only, and then move on to the update. So this is, you must have heard about it, this is a galaxy at redshift 14 observed with the JWST. They had a tentative detection of 3.6 sigma of C3, went and observed with ALMA, and bang, this is oxygen 3 shifted in band 6 at a spectacular 6.6 sigma detection with 2.8 hours on the sky, while with the JWST that needed 3.9 for a tentative detection. It's really, really spectacular, and also it also produces spectacular results. For example, the metal-rich environments at these redshifts that are quite unexpected, I'm told. We now are able to do kinematic studies at redshifts 7. So we are approaching or are already in the epoch reionization and are able to do, thanks to ALMA, kinematic studies of these objects. We can study the extreme environments of extreme sources. So basically probing the boundaries of the universe. So this is a work I was involved in. This is with Roman Fernandez Aranda and Tânio Dias Santo. Maybe some of you know him. So we observed what is currently the most infrared bright source in the sky. It's a hot dust obscured galaxy at redshift 4.6. with 7 out of the 8 bands that were available at the time, with all these amazing line detections, and then comparison to cloudy that gave us really extreme conditions for these extreme objects. This year also we had the first report for the first extragalactic protoplanetary disk, which you can see here, completely different science. But again, this is again a first that came this year with ALMA after 10 plus years of observations. Convective zones resolved in the surface of these evolved stars, again reported this year. What is this? I can't even remember what this anymore. Yeah, this is the confirmation of a supernova stage that was missing in the evolution of supernovae. It's a supernova that actually reignited or reshined, and these are observations in band 3 and band 6. So all of this provided, all these results came this year, the last year of ALMA, after all these years of observations. And this is now water in HL Tau that we saw before. There were recent observations in band 5 that found that there is the equivalent of 3.7 times worth the Earth's oceans in water in the regions where we expect to find the planets in these systems. So this and many, many, many more. So now you understand why I wasn't able to do an overview of all the science. This is just from the past few months, right? So ALMA is currently producing science at an exceptional rate, comparable to other facilities of the same maturity, and still producing not incremental science, but actually groundbreaking science as we speak and as you saw. So this is, this is the number of proposals that we receive per ALMA cycle since the beginning of ALMA operations in early science in cycle 0 all the way now. So we have stabilized over the last 5-6 cycles to something like 1,750 proposals that are coming in. This is requesting the 12-meter array, and then around 350 for the 7-meter, and around 150 in the TP array. So this include also, these are not standalone, these are proposals or requests, maybe 12-meter, but ACA as well, or standalone and top power as well. So it's really the demand on the facility is huge. We receive yearly about 40 something large programs. So large programs are programs that request more than 50 hours of observations under special conditions and whatnot. We are offering now joint proposals with our facilities, with JWST, VLA, and VLT, with ALMA as the main observatory, but also with ALMA as a partner observatory. So more and more things, the interest is still there in the community, and this results in crazy oversubscription rates. So as you know, the ALMA time is distributed among the regions proportional to the amount of funding that each executive put at the time of construction. So ESO and North America have about 31 and something% of ALMA time. And this makes it so that in Europe, the oversubscription has reached numbers that we haven't seen in any other facility. It's an oversubscription of 8 counted over the number of hours requested, not the number of proposals, okay? So the European community is asking 8 times more time on ALMA than ALMA is able to offer. So all these are good signs. Of course, it means that the facility is still, at its peak. It's producing, again, this is the publication rate over the year, broken down by science category. We're almost reaching 4,000. I did this plot yesterday. I was hoping that I would be able to show 4,000 up there, but it didn't work out, but we're almost there. So these are the total. So there have been almost 4,000 papers that have been produced based on ALMA data, be it archival or PI or a mixture, as you can see here, and almost half of which are led by EU-affiliated PI. So it's a lot more science coming out for the amount of time that is invested in ALMA from Europe. And here you can see that the workhorses of ALMA are, as always, bands 3, 7, and 6, or 6, 7, and 3 here. So the thing is, we're still producing great stuff, but also the astronomical landscape worldwide is changing. Okay, so there is a bunch of new facilities that are there or upcoming now, and many of them will address the same science questions as ALMA wants to address. So, which is basically the origins of galaxies, the origins of stars, and the origins of planets, so what we all want to know. So, in order to keep ALMA at the forefront of research, but also make it so that the synergies with these facilities are meaningful, and given that there is no replacement for ALMA in the horizon, it's impossible to get such a facility anytime soon. Well, we need to actually make sure that ALMA can keep up with everything else that is happening around it. And this is one of the reasons why we have embarked in this major upgrade, which we call the wideband sensitivity upgrade. Wideband, because as you will see, is all about doubling for the moment the bandwidth offered and sensitivities because of the electronics that will enhance the sensitivity of ALMA as we speak. And this means upgrading pretty much everything, as you will see shortly. So this did not come out of the blue, right? So all these things were in mind of the people, of the wise people behind ALMA since the very beginning. We knew that at some point we would have to do this upgrade. And therefore, the board of directors, the advisory committees, the community were all involved into building up what we call the ALMA 2030 roadmap, that actually describes what is needed to be done in order to keep ALMA at the forefront of research. So this is the, you can find this document online. It is a very, very short and to the point document. I invite you to read it so that you understand better what I'm trying to explain here. So basically, what I want you to remember for the rest of the talk here is that the vision in this roadmap was to broaden the receiver bandwidth, but by at least a factor of 2. This is what the WSU is about, and upgrade the associated electronics and the correlator. And the reason we want to do this, again, is driven by science and not by because we want. But now we have sort of upgraded the scientific question. So there are new science drivers behind this, this endeavor related to the origins of galaxies, the origins of chemical complexity, and the origins of planets. So what we want to do now is be able to trace the cosmic evolution of key elements out to redshifts, you name it, but within reasonable time. So at a rate of 1 to 2 galaxies per hour now. We want to be able to trace the evolution from simple to more complex molecules in nearby protostars at the rate of 2 to 4 protostars per day. And we want to image protoplanetary disks at a resolution of 1 astronomical unit. Okay, so this is really a huge jump with respect to what we were planning, what ALMA was supposed to be doing. And this is why it's currently impossible to do this with the way ALMA is built and functions, and with the technology that is behind it. Okay. So in order to achieve all these things, and as part of the ALMA development program, we are changing, as we speak, everything that sits between the antenna, the actual dish, and the astronomer. Okay, so everything in between is going to be upgraded one way or another. So the receivers are going to be changed, the digital chain is going to be changed, the correlator is going to be changed completely. This implies new data rates that need a new data processing system, so CASA or new CASA, or forget about CASA, we have to see. And this means also new archives to be able to host these new products that we will be serving to our community. Okay, so all of this is going to change and is already being changed. So how do we do this? This doesn't happen, overnight, and it doesn't happen out of the blue. As I explained, all this is a decades-long, well, years-long exercises. And what is interesting here is that the ALMA development program was part of the ALMA operations plan since the beginning. Okay, so there is a bucket, a budget that is dedicated to developing studies or projects within as ALMA operates, so that the time, when the time comes, which is now, we are ready to make this upgrade. So we're not starting from zero now, but we're starting from studies and projects that have already been developed over the years while ALMA was operating. So we divide this into two kinds of programs, let's say, the studies and the projects. So the studies are small, and they are intended as an initial exploration of concepts that will or might be of interest to ALMA at some point, short term or longer term. And these are funded and managed by the regions. The projects are much larger. We're talking about a lot of investment, and they have a specific deliverable in mind when they start. So when a project starts, it will deliver a band, for example, or something, a digitizer, a correlator, something. So the details of the implementations of this vary because of the differences in, mandates, funding scheme, whatever of the regions, but the general idea is what I describe here. Okay. So in Europe, we have the particularity that Europe is represented via ESO. So all the member states of ESO are within in ALMA via ESO, but ESO, unlike the other partners, does not have an inside facility to develop technology. So we rely on the community for developing technology. Okay, so the funding is coordinated via ESO and in collaboration with external institutes, etc., universities. There is a development of technology for the needs of ALMA. And this follows like a 3-year cycle. Every 3 years, there is a call for such development projects that the call is managed there by studies. The call is managed by ESO. It goes to the community. There is a expression of interest, and then this ends up in a list of studies that are happening right now. As we speak, here are the ones that are active right now that came out from the last call. So the call was at the end of 2023. By the time the approval process went on and the kickoff meetings and this and that, we started all of this at the beginning of this year, in fact. So it's a very slow and tedious process in order to even get started with the development of all these things. We also have small internal studies that are run by people that have sort of insider information about ALMA as an aside, but these are funded like at a very low level just for travels and meetings. And this I just put here because I don't know if you know the people, but you will see here there are people from ESO and from the various institutes that are running the projects and the studies. So indeed, these are very tight collaborations between ESO and its community. So currently, in Europe, we have 4 development projects ongoing. One is the digitizer, so this is part of the digital chain. There is the next generation observing tool, which is the NGOT. I'll come to that in a minute. This is actually an obsolescence project. It's not per se a WSU project, but it's needed for the WSU because the OT is a Java application. It's getting old by now, so little by little we need to get rid of it and modernize ourselves. There are the fibers that will bring the signal from the AOS to the OSF, because what I didn't tell you is that the correlator is no longer going to be up at the high side of 5,000 meters. We will have to bring it down to 3,000 meters, and this implies a lot of mess. And last but not least, band 2, which will be the first wideband receiver that will be a 16 gigahertz bandwidth. Its commissioning is happening, and we will deploy them by the, I think, 3rd quarter of 2026. All the antennas should be equipped with the new band 2, which encompasses in frequency also band 3. So at the beginning, it was supposed to be band 2, and then we keep band 3, but now band 2 covers all of band 3 as well, and the original specifications for band 2. So, I thought I had skipped the slides, but never mind. So then let me go through them. So the NGOT, as I said, is an obsolescence issue. Those of you that have used it, you must realize that with time it's becoming very difficult to maintain because of Java issues, because of security issues, because you name it, because the interface is getting very old. So now we're moving into a web-based interface that also gets rid of some of the limitations of the classic OT, as we like to call it, and hopefully it will become a lot more a lot easier or faster to run. So there are no memory restrictions anymore. There are some old technologies like the visual browser that's going to go away, etc., etc. And this is how the OT, so this is the field setup looks now, and this is the equivalent, how it will look a lot more sleek, say, and modern compared to what we have. And this is the technical justification. So the functionality is identical, but the look and feel is different. Some of the code behind has been updated. And once we move to this, the new WSU requirements are going to be implemented now in the web version and no longer in the standalone Java application. Band 2 is a collaboration with Nova, GARD, ENAF, and an AOJ. So it's a huge thing, of course. As I mentioned, it's going to cover the full bandwidth of Band 3 as well. And I already mentioned the timeline. Now, the nice thing here is that for the first time, the cryostat is full. All 10 slots are filled with all the bands. It's quite nice to see, in fact, after all these years. Digitizers, again, collaboration with the University of Bordeaux, and the fiber optics for the reasons I mentioned before. So I already said that. Let me just remind you what it means in terms of location of the things that we're updating. So the antennas are up at the 5,000 meters. The receivers are there, of course, and the back end as well. All of this is going to be changed. Whatever is in blue here is going to change. And then the new fibers will have to come from the AOS down to the OSF, because now the new correlator is going to go where the control room was. So the control room has to move, and there have to be new infrastructure for the correlator. And this comes also with many changes in the software, not only the OT, but also the scheduling, the telcal, the pipeline, everything. I can't repeat this often enough. Everything is changing. The outcome of this crazy change, nevertheless, is that we're going to gain in speed. So continuum imaging speed will increase by at least a factor of 3 for the ×2 bandwidth increase, which is the goal for the WSU. The line imaging speed is expected to improve by the same factor. And what's more important for some science cases is that it will allow for a very high spectral resolution observations without having to sacrifice, let's say, bandwidth. And I will come to this in a minute. So more in details, what is the WSU? What is happening? So first of all, the available bandwidth is going to double. Okay, so currently the ALMA receivers cover, they can observe in a range of frequencies, but you can at one time only set it up to cover up to 8 gigahertz. Okay, so maybe we can see it here. So this is a double sideband receiver. You have a sideband here and now a sideband here. These are the basebands. This is how you set up your observations. Each baseband can be up to 2 gigahertz wide. So at any time, you can cover up to 8 gigahertz. Okay, so the idea is that the new receivers can reach 16. So the yellow bars here that you see will be twice the width. Okay, so that's number one. Number two, the correlated bandwidth. So again, let's go to the OT. I find this better. So now if you want to do very high resolution, spectral resolution observations, you have to select very narrow spectral windows because the correlator cannot cope otherwise. Okay, so the higher your spectral resolution, the narrower your bandwidth. All of these are going to change because we are going to be able to correlate up to 16 gigahertz and down to ridiculous resolutions, 0.1 to 0.2 kilometers per second, you can still observe at 16 gigahertz. And all this directly, as I said, translates into speed. So you will be able to observe much faster whatever you will be doing, you were doing until now. And depending on frequency, the speed for the lowest frequencies will increase by a factor up to 70. Okay, so not a survey instrument yet, but getting there in order to be able to follow up sources and make new discoveries. Yeah, it's an example again from the OT, from the observing speed. So currently, if you want to cover a given spectral range, you have to do a spectral scan. This means in reality, different scheduling blocks. And then in the future, you'll be able to do this in a much faster. So there's an example, if you want for whatever reason to cover all of band 2 because you're looking for something that you know that it falls within this frequency range. Currently, you have to, depending on the resolution, set up between 209 tunings or 8 tunings if you want very coarse resolution. Well, with the WSU, you'll be able to do this with 4 tunings. And if we ever reach the highest, the goal of WSU, you'll be able to do this in 2 tunings, fill the whole band 2 in 2 SPs, let's say. There is also a number of changes, as I mentioned. This is about the bandwidth, so this is why it's called wideband upgrade. There's also a number of changes that will directly affect the sensitivity. So the receiver noise is going to go down. The correlation bits is going to go up. Now we're doing 2 or 4 at times. We're going to have a minimum of 6. The noise of the highest frequency band is going to drop significantly. And all of this will increase the sensitivity by about 20% currently. Now, I mentioned en passant the new correlator. I want to insist on this now. So the correlator, currently the ALMA correlator, is a computer that has done amazing things. Is the most powerful computer that has ever operated at an altitude of 5,000 meters, but it is getting old. Okay, so it's needed to be updated, upgraded, or changed even sooner rather than later. So now we will get the advanced technology ALMA correlator. My colleagues call it ATAC. I like to call it ATAC. So, and this correlator is going to be placed, as mentioned, down at the OSF, which also means infrastructural changes other than, in addition to bringing the fibers down and the signal and all of that. It has the ability now to handle the subarray. So currently we have a different correlator for the ACA, but this correlator can handle the 12 meter and the ACA and the TP, so all in one. It has a lot more spectral channels and a lot more basebands and all of that, but the numbers are so high that it will be impossible to offer the full flexibility to the community, because it's just impossible to offer the user the possibility to set up, I don't know, 80 channels at a time. So we have to find a compromise between what the correlator can do and what it is feasible on the user side to set up observations. So in fact, what we're doing now is upgrading everything, as I hope that you have understood, while running operations. Okay, so this picture was shown for the first time by Sergio Martin, who is the head of science operations in Chile. And in fact, this is exactly what we're doing. Okay, so we're changing everything while observing, not only observing, but actually for the first time ever in this cycle, we reached what we promised. ALMA is scheduling 4,300 hours with projects rank A and B. And for the first time ever, we almost reached this number in this cycle while we have already started the WSU. So it's crazy, but you know, we're doing it. I don't know at what price, but it's happening. But this inevitably cannot go on like this, because it will at some point, all these upgrades will affect the number of hours offered, the number of antennas offered. So as a user, you have to keep this in mind, that starting from cycle, maybe, I don't know, 13, 14, things are going to change in terms of what ALMA can offer. Still, cycle 11 that just started is a normal cycle. Cycle 12, for which deadline will be in April, will be normal, I think. So take advantage of it, because I'm not sure what's coming next. So I want to focus a bit on the reality of the science that is going to come out from these upgrades now, and starting with the origins of galaxies. So this is what this ALMA can observe. This is the CO transitions and the atomic lines as a function of redshift, as a function of frequency and band, basically. So in practice, what does it mean? What do these upgrades translate? So this is the example of that galaxy I spoke about, the redshift 9 point something. It was a dropout, and it was a candidate for that photometric with that photometric redshift, and it had a probability distribution of that redshift that looked like that. So in order to pinpoint the redshift of 9.11 that I showed before, the setup had to be done like this. And in fact, the redshift turned out to be not where the photometric peak was, but quite off. So hadn't they done this, they wouldn't have even seen it. So In cycle 3, we did this with 4 tunings. In ALMA 2030, we'll be able to do it with 2 tunings, so half the time, probably even less. In terms of chemical complexity, I chose a science case which I know nothing about, but I was actually impressed when I had a look at the paper. So in order to understand star formation, one has to look at the various components of this process, right? So in order to understand why some regions form clouds, some others don't, and why some stars are massive and some others aren't, and what determines the distribution of stellar mass, you have to look at the protostar, the envelope, the outflow, the disk, and whatnot. And in order to observe these components, you have to look for different molecules that emerge in the various regions. So this is a schematic from Lukasz Tichoniek's paper a couple of years back. So if you want to fully understand the process of star formation, you have to go and observe all of these molecules and understand how interpret the conditions in the various components of this phenomenon. So for this was done in, I think, 2 or 3 ALMA programs, which you understand it every time it jeopardizes. Okay, you have a program accepted, nothing guarantees that the next time you want to observe another molecule, you'll get time. They manage. So they sort of patched a couple of projects together over time, and they managed to get some idea of what's going on in these regions. But if we reach the ALMA ultimate goal of 4 times the bandwidth, what's going to happen is that in one single observation, they will be able to observe all these molecules and actually answer those non-trivial questions that I mentioned at the beginning. Again, this is just another example. And such examples also include, for example, this is a survey in protostellar binary. So currently what we can do is this at the time. With ALMA 2030, we can do this, and ultimately everything the same for the centers of nearby galaxies, etc., etc. So you get the gist, I think. Finally, for the origins of planets, again, this was from a couple of projects put together, different molecules that provided the conditions of the star formation around some young star. With ALMA 2030, we'll be able to observe about 4 times more molecules simultaneously. So really this upgrade is promising like revolutionary science, really transformative science once it's delivered to the community. So we have just started the WSU. So this started, let's say formally about 1.5 years ago, but we are already thinking of what's going to happen after 2030, okay? Because 2030 is just in 5 years down the road. So the ALMA 2030 roadmap already gave us some ideas of how ALMA could expand beyond the WSU. And this includes things that I think everybody has thought of at some point or other. Increase of the baseline, so maybe, I don't know, put antennas down at the OSF, who knows where else. Focal plane arrays, which would increase dramatically the wide field mapping. So, but this is technology yet to be developed. Increase the number of antennas, or adding a large single dish in the submillimetre to actually for the zero spacing, which is something that currently ALMA is suffering from. That last one in the roadmap was explicitly stated that this is not within the scope of the current ALMA operations. And this is why some of us put together a design study that was funded by the EU and just concluded in August 2024 to design this, to make a design study of such a 50-meter submillimetre telescope to be placed somewhere in the Atacama Desert, most likely very close to where ALMA is. And as we concluded, we also delivered a first design of such a telescope. So we're talking about 50 meters diameter, up to 2 square degrees of field, and a suite of 6 instruments that we are going to develop as part of phase 2, which is starting in January 2025. For another 3.5 years. So this is a second phase, again funded by EU, now Horizons Europe, in which in the first project the IAC was not involved. In this phase, the IAC will be involved, and it will be leading the operations and user experience work package. and the other work packages are a bit tied to what was done in the first phase, so telescope design, instrumentation, software, and energy. We want it to be a sustainable facility, a facility really of the future. So with that, I'm going to stop. But before I stop, I want to remind you all that we are going to have the ALMA days in February, 18 to 20, 3 full days dedicated to ALMA things. And by things, I mean, there are going to be talks about ALMA archive, ALMA tools, ALMA capabilities, the WSU, VLBI, joint proposals, everything. There are going to be a few hands-on sessions. So for those of you that have never used ALMA tools, this is your opportunity to actually get to use them with the experts next to you that they can help you out. So please register. The registration is open until December 15, I think, something like that. And I think with that, I would like to thank you all and everybody listed down here as well.
Thank you. So we have time for questions.
Thank you, Evanthia, for such an informative talk. Lots of things. So when you said at the beginning, I think you said that in the case of galaxies, it will be possible to look at CO, C+, etc. at cosmic noon in a few hours.
That's
2 hours.
That's the science drive. This is where we want to eventually reach. It doesn't mean that the day we deliver the WSU, it will happen, because, you know, this is a scalable upgrade, right?
Mm-hmm.
So there is a ×2 bandwidth deliverable, but there is also a 4 times the bandwidth goal.
Okay, because at the moment, for example, I think this year there was a large program for Galaxy had Redshift 2. And it was like, I don't know, like 40 hours per source to get CO, no? So, I mean, any improvement beyond that, it would be great. But yeah, if we could do this.
No, but this is why they're called drivers, right? This is where we want to reach.
Eventually, no? Not necessarily with this upgrade, no? So maybe adding more antenna or like in the future.
Well, as I said, I mean, the upgrade is scalable, okay? So pending technology and funding, more and more things can happen.
Okay.
Evanthia, I'd like to ask you about the annual budget of ALMA. I mean, the operation costs, and if you have numbers of other facilities, other similar facilities.
I'm not sure I can. Well, maybe these numbers are available in the annual reports. I don't know. In case they are not, I'll just give you a ballpark. We're talking about 3-digit million figures of operations.
Per year?
Hmm?
Per year?
Per year, yeah. So in the hundreds of thousands, if I'm not mistaken. I think I'm not mistaken.
And this upgrade, I mean, how much?
Wait, am I talking nonsense? Let me. Well, maybe I'm talking nonsense. Maybe it's a bit less than that.
And this upgrade, how much does it cost?
I don't know. I'm gonna say I don't know.
But it's not funded yet, or yes?
No. But that's the thing. So it's via the development program. These things are funded. So the correlator has funding. Okay, so the correlator is funding from the NSF. Is there. So whatever I spoke about is happening. So band 2 is happening. Digitizers are happening. The correlator is happening. The fibers will have to happen. What is not certain is what I just told Christina. So what goes beyond the WSU? So band 2 is happening. The next one is band 6. What happens after band 6? Well, spending funding, okay? But certain things are guaranteed.
And another question is, if you're interested in a particular line, the sensitivity is not going to change, no?
Well, it's going to change because of the change of the signal, the digital signal chain. So all the upgrades in digitizer, LNAs, and all of that are, and the lowering of the noise or the receiver noise, this boosts, let's say, the sensitivity.
By a lot, or
Well, the figure we're talking about is 20%.
yeah, thanks.
Hi, Evanthia. Thanks for this very nice talk. I have a question. You mentioned that band 2 will incorporate band 3 as well. So it will be from which frequency range?
Well, it will be, I think I showed somewhere, it will be.
I think it was a bit fast and I couldn't.
Well, it
catch that
covers the
fast.
full of band 3. I don't remember the exact thing. Well, let me. I'll find
Band
it.
3, I think
Put it
it's
back.
86.
Wait. You'll get it in a minute. Band 2 here. So 67 to 116.
And do you have any predictions of implementation of band 1 or?
But band 1 is already offered. That's
Is
it.
already
We have offered band 1 since March this year.
since this cycle?
Yeah.
Okay. And at some point you mentioned the sensitivities will increase up to 70% in band 8 and 9.
No,
Now
the
with the
sensitivity,
new,
the speed, right?
I think I saw somewhere that the sensitivity will increase in band
Or
8.
with the new, well,
the new-
if bands 9 and 10 are upgraded, so basically the new receivers will have increased sensitivities.
This would be amazing to see.
But if and
If.
when.
Okay. Thank you.
Okay, if there is no more questions, let's thanks Evanthia again. Thank you.